Neutron stars aren't dark matter, we figured that out a while ago. But new research suggests they might actually be dark matter factories, potentially producing axions, one of the leading candidates for dark matter. To fully understand reality, we need to comprehend its fundamental building blocks. The Standard Model of Particle Physics does a fantastic job of describing known particles, 3 generations of quarks and leptons, the bosons that carry the 4 fundamental forces, and the mass-granting Higgs particle. However, a few holes remain in the Standard Model that need to be addressed for a complete picture. One of these gaps is known as the strong CP problem, often called one of the most underrated issues in physics, likely because it's abstract and difficult to explain without math. But here's the gist: the strong force is expected to violate charge parity, CP asymmetry, meaning that flipping charge and mirroring, say, a proton or neutron, should result in a different configuration. But in quantum chromodynamics, QCD, it seems to return to the original state. The most popular solution to this problem is to introduce a new quantum field that eliminates CP-violating terms in QCD, leading to a new particle called the axion. Axions are popular as a dark matter candidate because they are elusive and only weakly interact with electromagnetic fields. If axions are to be dark matter, they must constitute around 80% of the universe's mass, a feat only achievable if they were produced in enormous quantities just after the Big Bang. Even if axions don't fully solve the dark matter question, proving their existence would address the strong CP problem and align with predictions from string theory. Detecting axions is difficult due to their weak electromagnetic interaction, but axions have an unusual property: they sometimes convert into photons and vice versa in strong magnetic fields. In theory, this could allow a light beam to pass through a solid wall by converting photons to axions and back with magnets. So far, experiments haven't found anything, perhaps because our magnets aren't strong enough. Current detection efforts max out around 10 Tesla, while the world record is 45 Tesla. However, in space, neutron stars, particularly magnetars, can generate magnetic fields near 10 billion Tesla, making them a promising site for axion production. Axions could theoretically form in neutron stars if conditions align. Strong magnetic fields and a high photon supply are essential. A more complex requirement is a time-varying electric field parallel to the magnetic field. In neutron stars, electric fields might arise from the star's rotation within its magnetic field, creating an alignment that could produce axions. However, nature resists parallel electric and magnetic fields, which could suppress axion production. Yet, neutron stars might overcome these obstacles. Their extreme magnetic fields co-rotate with the star, leading to helical magnetic fields trailing from the magnetic poles, known as the magnetosphere. Charged particles lifted from the surface can stream into space along these field lines, potentially allowing axion production to continue. While theoretical simulations are needed to explore these conditions, results indicate that neutron stars could produce axions in bursts, leading to fluctuating electric fields favorable for axion generation. Neutron stars emit powerful electromagnetic waves, like the intense radio jets of pulsars. If axions exist, they might explain both these radio jets and phenomena like fast radio bursts, FRBs. If neutron stars emit axions, they could convert to radio waves in unexpected directions. This would imply that neutron stars should continuously emit across a range of radio frequencies. Observations, however, show that pulsars generally emit only regular blips in their radio beams. This lack of continuous emission has allowed scientists to place constraints on axion existence using data from 27 nearby neutron stars. Another detection method involves trapped axions, which may fall back to form a dense cloud around the neutron star. This cloud might help explain pulsar annulling, temporary suppression of radio emissions, or produce narrowly ranged radio emissions that previous searches could have missed. When a neutron star's magnetic field fades after millions of years, these axion clouds might release energy in bursts that resemble FRBs, which have perplexed astronomers. Future facilities like the Square Kilometre Array may reveal radio signatures indicating axions, providing new insights into dark matter. Although neutron stars alone likely don't produce enough axions to account for all dark matter, their potential to generate them offers a means to study dark matter if axions are indeed a component. In summary, while axions remain hypothetical, neutron stars could be prolific producers of these elusive particles, possibly explaining phenomena like pulsar jets and fast radio bursts. If axions exist, studying neutron stars could advance physics beyond the standard model and bring us closer to understanding dark matter.